Okay, now let's use our understanding of matter to investigate how much energy you can store and use from various objects. So let's start off with a proton, and we'll drop an electron in until it gets to our atomic size, about 10 to the minus 10 of a meter. How much energy does it liberate if you drop it in, or equivalently, how much energy would it take to pull it out? Well, if we ignore the quantum mechanics for the moment, that's just the electrostatic energy, which is given by the equation minus Q1, Q2 over 4 pi epsilon naught R. So if you plug in the charge of an electron and a proton up here, and 10 to the minus 10 of a meter over there, that comes out as about minus 2 by 10 to the minus 18 joules. So that, if you like, is a sort of characteristic energy associated with ripping an electron out of an atom or dropping an electron into an atom. And it's a pretty small value, if measured in joules. For these sort of small atomic energies, we actually use a different unit called the electron volt. Now, an electron volt is how much energy an electron acquires if you accelerate it over a potential difference of a volt. And it's got a numerical value of 1.6 by 10 to the minus 19 joules. So measured in that, this characteristic energy is about minus 14 electron volts. Now, this is something we can measure experimentally. You can actually measure how much energy you get ripping an electron out of the ground state of a hydrogen atom, and that turns out to be 13.6 eV, in extremely good agreement with this. So that is about the sort of energy you get to rip an electron out of an atom or drop one in. Now, how would you expect this to differ for different atoms? This is hydrogen, one proton, one neutron. Well, I imagine if you had some other atom with lots of protons in the middle, you might expect the charge here to be bigger and therefore the electric field to be bigger. And that would be the case if, say, you had an iron nucleus with all the electrons gone and dropped one electron in. On the other hand, a much more normal situation is where you've still got most of the electrons here, you're just missing one, and you drop one extra electron in. So in that case, I'd expect the energy to be about the same as this. Now, that's the energy needed to rip an electron out, ionize an atom. How about chemical bonds? Well, in a chemical bond, you've got two atoms, and if it's an ionic bond, you've got atom 1, atom 2, and they swap electrons, so the electron has to come out of one and go into the other. So I'd expect the energy to be about the same for that, maybe a bit less. Covalent bonds are a bit more complicated because you're sharing electrons between things. But nonetheless, I'd expect the energy to be roughly the same or a bit less than this, maybe a factor of a few less than that. So I'd expect this sort of order 10 eV or maybe less, maybe 2 or 3 eV to be the characteristic energy of most bonds. Is that actually correct? Well, let's check. There's trespassing into chemistry here, exciting really. Chemists are very good at working out how much energy you need to break bonds or create bonds. For a bond between hydrogen and carbon, for example, the energy is 411 kilojoules per mole. That's a rather different unit from what we've talked about, which is joules or electron volts per bond, but we can do that conversion. A mole is, by definition, Avogadro's numbers worth of atoms or molecules, which is 6 by 10 to the 23 molecules. So if you've got 1 mole here, that means you've got about this many bonds, roughly speaking. So the energy per bond is going to be roughly 411,000 kilojoules there, divided by 6 by 10 to the 23, roughly speaking. We've glossed over the fact of whether it's a mole of carbon or hydrogen and exactly how many bonds are involved, but that's only factors of 2 and things don't matter so much. And that comes out as about 7 by 10 to the minus 19 joules per bond. And if you remember, we worked out a characteristic energy of about 2 by 10 to the minus 18, as opposed to 7 by 10 to the minus 19. So that's only a factor of about 3 or so off. So this is about 3 times less, which Ninja is pretty good. So it seems to work. This energy of about 10 to the minus 18 joules seems to be a good characteristic energy for a chemical bond or a ionizing an atom.